Hey y'all, we are Memphis Communiversity and we're back for another Calculus Done Wrong lesson where we wrong calculus before calculus wrongs us. Today we're going to be starting a new unit, area and volumes, and we're going to be doing the first lesson, which is just area. So keep in mind that area questions do have a little bit of variation, but it's going to be the same thing every time. We're going to be doing integrals of sort of differences of functions. So keep in mind that we're going to be doing very standard examples in this video, but we're going to switch it up a little bit. We're going to do the ones that have a little bit of a harder integral. We're going to do some that maybe involves doing y's instead of x's. We're going to do some that involve calculator. And then finally, for the last one, but just the last one, we're going to do unbounded region, which is just a BC topic. But everything before that is an AB topic, so let's get started. Let's do area. So before we start, let's sort of go over the process. The process is fairly simple. So keep in mind that we're not using area to compute integrals. That was a previous video. What we're actually doing is using area to, using integrals to find areas of regions. So for example, let's just keep it generic for now. Let's say we have a function f and a function g. So f is my top function, g is my bottom function. I'm going to cross at a and b. So these are the x values for the intersection. I don't know what I'm saying anymore. So what we're going to do is, if you can see, f and g sort of go on forever, but they certainly enclose a region, this region right here. So we're going to call that R. And what we're going to try to do is find the area of R. So the way I like to think about it is I like to draw a rectangle. Sometimes my students don't understand why I like to draw this rectangle, but I'm going to draw a rectangle called a dx rectangle. It helps me remember everything has to be in terms of x's, and it'll help me when I do the process. So keep in mind that what we're going to try to do is we are going to use integrals again to find the area. And the way it works is that we're going to be integrating the vertical distance between f and g. Because if you have the vertical distance of f and g, and then you do it and sum it up for every single x value, you're eventually going to have area. Imagine if this is just thin lines. So this is the vertical distance between f minus g. This is the vertical distance, this is the vertical distance, this is the vertical distance. As you get them closer and closer together, and they're thinner and thinner and thinner, notice that eventually you will have this area. So the process itself is not that bad, especially when you have a calculator, so you don't have to do any integrals yourself. But the process is the integral of top minus bottom. And I like to draw my original dx rectangle because it's really easy to tell what the top and bottom is based off that dx rectangle. So the top of the dx rectangle is literally touching the top function. So in this case, dx is touching f, so that's going to be our top function. And then finally, the bottom function is whatever the bottom of the rectangle is touching. So in this case, it's touching the g of x function, so that's going to be the bottom of our rectangle. So this is what we're going to try to integrate. We do need numbers on the integral, we need limits on the integral, and keep in mind that if you're dealing with x's, you're just going to do the leftmost x value and the rightmost x value in the region. So it looks like the leftmost x value is a, and the rightmost x value is b. So it's going to be a and b. So that's going to be our formula. This is the formula we're going to use a lot, top minus bottom, where top in this case is f minus g. So keep in mind that sometimes everything will be in terms of y's, but it's going to be the same thing, except the integral will be tweaked a little bit. Instead of the integral of top minus bottom, and you go for x values, because everything is going to be turned to our side here, we're going to do the integral of right minus left, and then everything will be in terms of y values. But that doesn't happen very often. That's going to be our third question, I believe. But let's get started with more standard examples, and we'll eventually get there. So the first question I'm going to do is this question right here. I'm going to list out the functions for this question. Y is equal to minus e to the x plus 3. Y is equal to x minus 1. We also have the vertical line x equals 1. So sometimes they give you these vertical lines to cut off the region. As we did in the previous one, that region was naturally cut off by the intersections. The functions themselves form some sort of interval region, but sometimes they're sort of unbounded, so you need to cut it off by vertical lines. So in this case, we're going to have these are going to be the sides of my region. And what I would say is don't focus on the picture, because oftentimes the graph is already provided or you have a calculator. But in this case, the graph is going to look like something like this. It's going to be this line right here. I think this is e to the x plus 3. You're going to have x minus 1. So it's something like this. Not perfect, but that's good enough. Sort of a small picture, but I think we'll be able to work with this. So notice again that the x equals 1 and y equals 1 helps us bound this sort of region. So notice the x-axis is or the y-axis, I keep saying the x-axis, but the y-axis, it forms part of the region. Same thing with the line y is equal to x minus 1, and also the line negative x plus 3. Keep in mind, we're not going all the way to the intersection point because we don't know what the intersection point is. We're just going to cut it off at x equals 1. So we're not going to have this little triangle part as part of a region, but that's perfectly fine. And what we're going to try to do is we're going to try to find the area of this region. So it's not that bad. To set up the integral, all you have to remember is the integral of top minus bottom. So I still like to draw my dx rectangle. It just helps me remind myself that everything has to be in terms of x's, because again, eventually it might be in terms of y's. And it tells me what the top function is pretty easily. It's going to be this one right here. We need an e to the x. And then it's going to be the bottom one is going to be the x minus 1 line. So let's get started. So it's going to be the integral, again, of top minus bottom. That's all it is. So we're going to put top in parentheses, minus e to the x plus 3. And then it's going to be minus the bottom integral, which is just the line x minus 1. So it's going to be minus x minus 1 dx. And then we're going to integrate for x value. So it looks like our first x value is going to be 0. And then the rightmost one is 1. So this is the integral. I'm going to do the integrals fairly quickly because we're not focusing on integrals in this video. But this is the integral you're going to try to compute. Potentially you might have a calculator. So this is going to be equal to the integral from 0 to 1 negative e to the x. Just going to simplify a little bit. This is going to be minus x plus 3 minus 1. Just be careful with your minuses, of course. You want to put your bottom all in parentheses so that when you have a negative, it'll distribute. So it's going to be plus 4. And we can quickly do these integrals. Again, we're not really focusing on this, but it's nice to review integrals as you learn this. So it's going to be negative e to the x, because the integral of e to the x itself. It's going to be minus x squared over 2. Then we're going to be plus 4x, because the integral of 4 is 4x. Then we're going to do fundamental theorem of calculus, plug in top minus bottom. Again, this work isn't as important as just setting this up, but it's going to be minus e, looks like it's going to be minus 1/2, because e to the 1 is e. And then when you plug in 4, it's going to be plus 4. We'll plug in 1 to get plus 4. And then just be careful, sometimes when you plug in 0, you're not going to just get 0. So in this case, that seems to be the case, because when we plug in 0, we'll get minus 1. So it looks like my final answer, if I quickly do math, is going to be minus e. 4 minus 1/2 is going to be 7/2, and then we're going to add back 1. So I believe the answer is 9/2. Let me try to make sure that is right. So 4/2 is 8/2. 8/2 minus 1 is 7/2, and again, we're going to add 1, so that's 2/2, 9/2. So that is the answer. But again, don't focus too much on the fundamental theorem of calculus. I'm sure you know how to do it. Usually teachers teach area after integrals because you need integrals, of course. But we did focus on this formula right here. And again, just let me remind you what it is. It's just the integral of the top function minus the bottom function, and you just think about what x values was this region. So again, keeping in mind that the leftmost x value, because of the given that we are bounded by the y-axis, is this line right here. That's represented by x equals 0. Furthermore, it's bounded by x equals 1. Again, we've cut it off. We didn't use this intersection point. We could have easily used the intersection point, but in this case, in terms of the wording, we bounded it at x equals 1, and that was it. And then we took the antiderivative, plugged in top minus bottom, and that's how we went for it. So let's just do a harder example, and then we're just going to do more examples, and more examples. So my next function, I believe, is going to be able to be bounded by the function, so we're not going to have any other things. It's going to be a weirder function, just as a way to practice integrals. Y is equal to 2 minus x, and then y is equal to 1 over 1 plus x squared. So this is going to be my next guy. I believe this picture looks like this. 1 plus x squared, I think, looks like this, maybe. So this is going to be 1 over 1 plus x squared. And then 2 minus x comes in like this. I don't know if I can draw a good picture. It goes like that. So this one right here is 2 to the minus x. So the somewhat parabola looking thing is 1 over 1 plus x squared. And then 2 to the minus x is this thing. So notice that this does form a region. Looks like we're having a little bit of a smaller region. It's going to be this little slit right here. So we're going to try to find the area of that. So keep in mind, again, I like to draw a dx rectangle. As you'll see, when we draw the next one, this is why a dx rectangle is nice to draw in this one. So we do need to find intersection points. Don't really focus on the intersection too much. A lot of times, again, these questions are calculator. So what you're going to be doing is either the solve button or graphing to find these intersection points. You're not required to find the intersection points. or potentially the intersection points are just given to you. In this case, I'm just going to note that 0 and 1 are the intersection points, if you can spot it. So notice that at this value right here, x is equal to 0, that solves both functions. 2 to the minus 0 is 1, and then 1 over 1 plus 0 is 1. The other intersection point is going to be 1 as well, x equals 1, because notice that when you plug this in, you're going to get 1, 2 to the negative 1, that's 1/2, and also 1 plus 1, which is 1/2 as well. But again, what I would not focus on is trying to find these intersection points. Potentially, you have to do algebra. We'll do algebra in the next one as well. Usually, the points are given or you have a calculator, and as long as you can use those tools to find the intersection points, you'll be good in a lot of the cases. What we're trying to focus on right now is just trying to set up the integral. So even if we have a small picture here, notice that we can still have a top function and we still have a bottom function. So just be wary. I like drawing this rectangle because the top of the rectangle is touching the top function. So if you're really sort of careless here, you might switch them around. So notice the top function is going to be whatever this line is touching right here. So it's the parabola looking thing. So it's actually going to be the 1 over 1 plus x squared. So it's 1 over 1 plus x squared. We're doing top minus bottom. So the bottom is going to be the other one. It's going to be the reverse exponential one. So 2 to the minus x. And then theoretically, you might type this in a calculator. But for now, what we're going to do is we're going to actually integrate it, perhaps trying to review integrals. So it's going to be 0 and 1. So hopefully you see that the setup of these questions isn't too crazy. It's just the integral of the top function minus the bottom function, and then you have the x coordinates within the region. Now let's review a quick integral just as a way to practice. What's the integral of 1 over 1 plus x squared? Well, that's an integral you should know. That's inverse tangent x. Finally, what's the integral of this one right here? Well, this one's a little trickier. If you needed to, you can u sub it. But first, let me remind you that this is not the power rule. This is the a to the x rule. So the derivative of a to the x is a to the x times ln of a. The integral of a to the x is a to the x over ln of a. So in this case, it's going to be 2 to the minus x over ln of a, 2. But chain rule and u subs are on both the AB exam and the BC exam, so you want to be wary of that. How are we going to find this guy to finish it off? Well, we do have to account that the derivative of the inside function is minus, so we're going to have to multiply by the reciprocal of that because we're doing a u sub. So in this case, the final antiderivative will be plus, because it's going to be minus minus, where one of the minuses come from that u sub. Then to finish it off, again, not the most important thing, but we're just going to plug in top minus bottom. So it's going to be inverse tangent of 1 plus 2 to the negative 1. It's just going to be 2 to the negative 1 over ln of 2 minus, we're going to plug in 0 plus, and anything to 0 is 1, so it's going to be 1 over ln of 2. So it looks like my final answer, again, I don't really care about it too much, is going to be inverse tan of 1. That's pi over 4. Again, a nice little question that reviews both integrals and unit circle stuff. Well, inverse tan of 1 is pi over 4 because tangent of pi over 4 is 1, because on that unit circle, the legs are the same. So it's going to be pi over 4. Then inverse tan of 0 is 0 based off the unit circle because tangent of 0 is 0. So finally, it looks like we have plus 1 over 2 ln of 2 minus 1 over ln of 2. But if you have 1/2 of something minus the full thing, which is this situation right here, you're just going to be left with minus 1/2 of that thing. So it looks like it's going to be pi over 4 minus 1 over ln of 2, 2. So we're going to leave our answer like this. I feel like this is a pretty simplified form. But while we are reviewing some things, we're reviewing unit circle things, we're reviewing integrals as well, the thing I want you to focus on the most is just the process. So again, if you have your picture, that's great. Usually these questions have a picture provided. And then when you integrate, just draw that little dx rectangle, integrate from top minus bottom, so top minus bottom, and then don't forget to change the numbers. You need numbers on the integral, and usually they're, if you have this dx rectangle, they're going to be x values. As we'll see in the next one, when we have a dy rectangle instead, we are going to be doing y values. So just be careful. Usually when you have a calculator, the best sort of course of action is to find both coordinates of the point, because potentially you might need both coordinates of the point throughout the question. But this is another nice area question. Let's go for that sideways question that we've been talking about a lot. So I'm going to erase this. So I'm going to erase this, and I'm going to do the function if I can see my computer screen correctly. I think it's going to be y squared equals 1/2 x squared plus 1. And then we're going to have y equals, let's see, what do I want? 1/2 x to the minus 1. So let me quickly draw a picture of this one. So this guy right here, do I want this? No, I do not. Let's see. I do not want this squared. So notice that this is a rare question in your high school math career where it's not a function of x. This is actually breaks the vertical line test, this parabola right here, because this is going to be a sideways parabola. It's going to look something like this. Then this line right here is going to be crossing through the point -1. Does this go? So I think it goes something like this. I'm going to draw it precisely. So let's see here. So when we plug in 0, you're going to get 1 and -1. So I think it's going to look like this. Not my best picture. This is a nice bold dot. So we have this. And this is going to be my function. So let's try to do the same thing we did in the last one, and you'll see why we cannot do it. And it's because everything is sideways. Usually our functions are going to be in terms of x's, but in this case, the function is in terms of y's. So if you notice, this function doesn't even pass the vertical line test. Again, it's a function in terms of y's. So if we try to do our rectangle business, our top minus bottom business, it's going to be okay over in this region because the top will be the sideways parabola, and the bottom, it's going to be this line. But over here, it's not going to be okay. So notice if I draw a rectangle like this, just like I did in the previous ones, where I try to do top minus bottom, it looks like both the top and the bottom is the sideways parabola. And we're definitely trying to avoid this situation. If you go back and look at the pictures that we drew in the previous 2 questions, top and bottom were very consistent. The top function, no matter where you drew this little rectangle along the region, was always one function. The bottom of the rectangle was always one function. So this is the case, and it's pretty obvious that it is this case because we have a function in terms of y. This is the case where you need to draw a dy rectangle. So I'm going to draw a dy rectangle, which is just the same thing but sideways. So it's going to be vertical instead. And then we're going to label it dy. I like to label it dy because it helps me remind myself that everything has to be in terms of y. So that's the first thing I'm going to do actually. When I express these functions, I'm not going to express it as some things with x's. I'm going to solve for y and express it in terms of y's. So this first function will be easier to express x in terms of y as opposed to y in terms of x's. Because if I bring the plus 1 over and I multiply by 2, looks like I'm going to get x is equal to 2y plus 2. So I'm going to label this line 2y plus 2. Again, when I'm about to do my top minus bottom business or whatever is equivalent to top minus bottom, I'm not going to use this name for the function. I want to be everything in terms of y's. That's why I like to label it this as a dy. It's going to be 2y plus 2. So if you solve for this one right here, well, it looks like we're going to, again, subtract 1 and multiply by 2. So this function, the name we're going to use throughout the question is going to be x is equal to y squared minus 1 times 2. So let's do 2y squared minus 2. So these, again, are going to be my 2 functions that I care about. So now I'm going to try to go over the formula. So again, everything is sideways if you want to tilt your head sideways and look at this function. So if you tilt your head sideways like this right here, then you'll notice that if I do tilt my head sideways, top minus bottom goes in this fraction. So it's going to be top minus bottom where you have these sort of y's. So when you're doing with anything with y's, it's no longer top minus bottom. What it's going to be right minus left, because right minus left is really top. So now let's do this y integral. I'm going to rewrite it and simplify it a little bit before we take this integral. Usually that's a good rule of thumb. If you have to do this by hand, another thing you have to be wary of is that we're using y coordinates. I like to have the biggest power first. So let's solve for some y coordinates. What we need to do is we need to find the intersection points and then finally things why we're doing y values instead of x values and minus 2. So it's a previous 2 question, which so it is kind of annoying to do these x values. Nice. In this case, we're going to be using y values. So let's do the power. So let me try to do this solution right here, and then we'll remember that the power rule says you add 1 to your exponent. Looks like it's not that new exponent. So in this case, it's going to be minus 2. It's going to be 2 y cubed over 3. So then the integral of 2y is just y squared. And finally, the derivative or the antiderivative of just the number 4. Usually it's 4x, but because I'm integrating everything by y, again, I'm just trying to find the coordinates of the 4y. This function then I'm going to plug in 2 and negative 1. Hopefully I'll have enough space here on the bottom. Be careful, just like when you take normal integrals, you want to be careful if you're negative. This point right here, do fundamental theorem of calculus, plug in the top thing, minus plug in the bottom thing. This point right here, the y coordinate is 2. So keep in mind, again, I like the y coordinate. It's going to be 2 cubed, which if you want, you can easily find the x coordinate. Negative 6. Looks like if we plug in 2 here, you're negative 16. Yes, that's right. Looks like if you plug in negative 1, you are going to get question myself there. When we plug in 2 here, it's going to be 2 plus 4. But that's the key. 2 times 2, which is 4. When you do these functions, you do want to find the intersection points. And finally, when I plug in negative 1, that should go a little bit better. Negative 1 cubed is negative 1, so once you have the intersection points here, you want to make sure you put the right negative 1 squared. That gets rid of this one as well. As we set up this integral, which is the most important part of this question, just setting up the integral. So now what we have to do is we're doing top minus bottom. You're doing x coordinates. So we label it with this. Let's try to compute all the things that are not in this question. We're going to use y coordinates. 4 plus 8. So instead of writing 0 to 6, and again, you're being careful with these negatives. It looks like in this case it's negative 3, but it's negative 3. Finally, so it looks like we are again with to set this up, to finish setting it up. The most important step. It is right minus left. So if you look at this, again, the line is right. And we're not going to use the name of the function because we want everything to be minus 16 thirds minus 2 thirds. This is not the most important thing, but we're almost done. So this question, minus 16 thirds minus 2 thirds is minus 18 thirds. So it's going to be 2y plus 6. So it's going to be 15 minus 6. Then when I'm doing left, I'm going to do this final answer of x in terms of y. But again, everything past here is just the integral, so that's not the new thing. So when I review this, I'm just going to review. And now we're going to do this integral. So again, this is an area question where everything is sideways, because we have this sideways parabola. So you cannot do top minus bottom, because over here in this region, top and bottom is the same function. And so if you did top minus bottom, you wouldn't know what to do. You would get 0. So don't panic though. What you have to do is you have to change everything to be in terms of y's. So the first thing we did is we wrote this function and we solved for x so that it's in terms of y's. In this case, it's going to be x is equal to 2y squared minus 1, and then this line was 2y plus 2. So then we were ready to set up the integral once we found the intersection points as well. Sometimes we do that with a calculator. Nice to find both coordinates, but again, when we write this dy, it helps us remind ourselves everything has to be in terms of y's, this negative 1 and this 2. So when we set up the integral, that's why we use y coordinates, and we didn't use top minus bottom because that's for x's. We did right minus left. So it's going to be right minus left. Keep in mind though that there's different names for these functions, like this line has 2 different names, but we found this name right here to be in terms of y's, so we're going to use that one because everything has to be in terms of y's. So it's going to be right minus left instead of top minus bottom, and you're good to go. So these area questions do have some sort of variation, but hopefully you see that the variation is pretty similar as you go across variations. For the x's, do top minus bottom, and then do x coordinates. And then for the y ones, do right minus left and do y coordinates. So let's do a few more questions, another few wacky questions that they might ask, and then we'll do that last one for BC. So 2 more sort of questions, or at least 2 more graphs, and we are going to be good to go. So the next question is actually going to be a calculator question, and obviously the calculator makes questions pretty easy. We don't have to solve equations by hand or find intersection points by hand. We don't have to integrate by hand. All we can do is just type it in a calculator. So as long as we can get the setup, we should be good to go. So in this question, what we're going to do is we're going to have the region f of x, which is ln of x squared plus x plus 1. And then we're going to have another function g of x, which is x squared minus 2x. So in a calculator question, if the graph isn't provided, then just you graph it into a calculator, graph both of these functions just to get a right idea. So I don't know what this top function looks like. I know x squared minus 2x, that's a parabola. Is that like so? But this top function supposedly, again, I typed it in a calculator and it looks something like this maybe, where this point is an intersection to origin, but we do need to find this point. So usually the first thing you do when you have an area and volume free response question and everything is already provided, what you want to do is you want to find the intersection point, because you're going to have to use the intersection point eventually. So in this case, it looks like our x coordinate of the intersection point is going to be x is equal to 2.86, I believe, 902. I think that's right. If I can see my computer screen right, I think that is right. So again, I found this with a calculator. So you have various options to find this. If you have a fancy Inspire with a computer system, what you can do is you can set this to be equal to this using the solve button. But if you have a calculator like the 84 or the 83, what I like to do the most is I like to graph the functions and use analyze a graph, use the calculator to find this intersection point precisely. But once you have this intersection point, hopefully you see that the question is pretty easy. It's unlike the previous one. Notice that this region is better than the previous one because if I draw any sort of dx rectangle, any sort of vertical rectangle, the top one is always this line right here, which is f of x, and the bottom one is g of x. So notice that no matter where I draw this dx rectangle, even if that one's a little fatter than the other ones, it's always the top of these rectangles are going to be f of x, the bottom is going to be g of x. This is unlike the previous question where the top and bottom was the same function in some parts of the region. So now we're actually ready for the question because the question isn't too bad. So what we're going to do is we're going to write the integral, of course, and then it's going to be the top function minus the bottom function. So in this case, the top function looks like it's f of x. If you wanted to, you could write ln of x squared plus x plus 1, of course. The bottom function is going to be g of x. And then we go for the numbers. Because we have everything in terms of x's, we're going to use x coordinates, 0 to this number right here that we found earlier using a calculator. If you want, I encourage you to actually try to practice finding this number with a calculator. Finally, how do you do this? Again, using a calculator to solve this. Let's actually write what you would type in a calculator because we don't actually have to do this integral. Just be careful again of being careful with negatives. So it's top, so it's the ln of x squared plus x plus 1. But when I type this in a calculator, usually I have bottom, all of bottom in parentheses. So that I'm sure that I don't have the wrong answer. So again, it's going to be x squared minus 2x all in parentheses. You need the minus 2x to be also subtracted. So supposedly when you type this in a calculator, you're going to get the number 4.399. Remember that on the AP exam, you cut every single decimal place 3 places after the decimal. But this has been an easier question, again, because we had a calculator. Let's do an additional question that they sometimes ask with these area questions. So let me sort of erase my dx rectangles so that we have a better picture of what we're going to go on. So what we're going to do is we're going to do the equal area question. We're going to remember this number. So let's remember this number of 4.399. And we're going to do an additional question, which is usually part D or part C of these questions. And what it says is that there's going to be some sort of vertical line. So a vertical line, usually it's given by K for some reason. X is equal to K, divides the region we care about. So my nice region, hopefully I can outline it a little bit better. But this region right here, where F is the top and G is the bottom. This vertical line divides our region into 2 equal parts. Divides region R into 2 equal areas. Or 2 equal parts, I guess. So what they ask you to do is write but do not solve an equation that gives you K. And this equation will involve integrals. So again, we don't have to solve the equation. All we have to do is set up the equation and we can just leave it like this. So it's going to be a one-line thing. And how it works is, notice that when we have this area, it's not going to be split in two midway between this point and this point because our region is not symmetrical. So it's not that easy. Basically, there's going to be some line K. I don't know exactly what it is. I probably didn't draw it correctly, but it's going to be some line K where this part of the region, I'm going to call it B, is equal to the first half of the region, A. So there's actually various ways you can set up the answer, but I like to do it in sort of 2 ways. So the first way we can do it is just say we want to find this line K. So we're going to have, this is X is equal to K. We want to find it where the region A is equal to the region B. So let's try to express region A and region B together. So what's the integral of region A? Well, it's still top minus bottom. So it's going to be f of x minus g of x dx. And what are the x coordinates though? That's the important thing. Well, in region A, it looks like our first x coordinate, our leftmost x coordinate is 0. So it's going to be 0 on the bottom. And then what's our rightmost coordinate? Well, this line x is equal to k is dividing the question. So at the top here, it's going to be a k. Now let's do the same thing for region B, because this is the area of region A, and we want to set it equal to the region of B so that they're equal to each other. So the area of region B looks like it's going to be, what's the leftmost point? Well, that's going to be K instead. And then finally, what's the rightmost point? Well, it's this point we found earlier using the intersection of the graphs. It's going to be 2.86902. Finally, what's in the function? Actually, in the function, it's the same thing because it's f minus g. So it's f of x minus g of x dx. So this is the answer to the question. Sometimes people get confused because you're not actually solving for this. But again, usually the words do not solve the equation, just write the integrals are usually attached to this question, the vertical line question where the k divides the region in two equal parts. So basically what this is saying is I want my first half of the region from 0 to whatever number you want me to find to be equal to the second half of the region, whatever that number is, to 2.806, whatever. There's other ways to express this, so I'm going to quickly write that. Another way to have this perfectly valid answer would be to have this region A. So it's going to be 0 to k of f of x minus g of x dx. And instead of setting it to the second half, what we can do is we can set it to half of the entire thing. But we actually found half of the entire thing. It's the integral from 0 to 2.86902 f of x minus g of x. So if you wanted to, you could write 4.399, which was the area of the entire region divided by 2. And this is another perfectly valid answer. So again, let me try to explain this. When you have the vertical line k question, it's not that bad because it's set up every single time in the same way. There's various ways you can answer it. Your answer will have an integral and it will be involved in an equation. So this first answer, a lot of students like to put because it's first half of the region equals the second half of the region. Notice that no matter how you write it, f minus g is going to be the answer in the integral because always, no matter what part of the region you're doing, the left half, the right half, or the entire region, f is the top and g is the bottom. So it's going to be f minus g. The things that's going to change are the x coordinates because those are the things that are changing within the region. So it's going to be 0 to k, and then k to 2.86902. So again, it's the first region, the first half of the region equals the second half of the region. This answer on the bottom here is also perfectly valid. What this is saying is you want the first half of the region from 0 to k to equal the entire area divided by 2. So because then you would have a perfectly split point. So that's how you do these sort of equal area questions. They do appear, and actually if you know what you're doing, you're going to be sort of comfortable with these questions because they don't really change too much. So that really concludes our area portion, or at least the AB portion of our sort of area topic of this video. Keeping in mind that, of course, everything before this was also BC as well, but there are sort of some questions that are BC only. So if you're an AB, you can stick around. It will only be a quick little question before we end the video. But if you're in BC, sometimes they ask unbounded regions, especially in the multiple choice, but even in the free response questions sometimes. So I'm going to do one unbounded question and we'll be good to go. So let's say we have the integral, or the region. Let's say we have the region this, and our function is this guy right here. We're going to call it e to the minus 3x. And basically what's happening, maybe I need to make it a little bit, hug the x-axis a little bit faster, so it's going to look like this. So we have this nice function, f e to the negative x. Keep in mind that this function goes on forever, and it never touches the x-axis. It gets really, really close to the x-axis, but it never touches it. So what we're going to do is we're going to try to find the region R, and the region R is going to be bounded by this function, e to the negative 3x, and also the x and y axis, and x-axis, y-axis. But again, why is this BC only? Because this region goes on forever. It's unbounded on the right side. So on the top, it's bounded by f, on the bottom, it's bounded by the x-axis, and on the left side, it's bounded by the y-axis. On the right side, it goes on forever. And what's remarkable is that we can have a region that goes on forever that still has finite area, because basically this function is getting so close to the function that even if it goes on forever and it never actually touches the function, you're not actually adding that much area after you get past a certain point. So again, what we're going to try to do is we're going to try to find the area of this region R. So it's the same thing as normal. What you do is you want to draw a dx rectangle. Looks like this dx rectangle is going to work because the top and the bottom is consistent even as you go on forever. So it's going to be the integral of top e to the minus 3x. Keep in mind that sometimes the bottom is just 0. So that's a pretty good example to do even in an AB one. Sometimes it's just minus 0. We definitely don't complain about that. The bottom is the x-axis. That's the line x equals 0. Finally, we have to choose the points, and this is where it gets kind of weird. So it looks like my leftmost point is not that weird, it's just 0. But the rightmost point, because we're going on forever, is actually going to be infinity. So now all you have to do is you have to take this integral, keeping in mind that this is going to be an improper integral. Watch our improper integral video if you need help with this. This is a BC integral. So let's just finish this off. We're going to write the limit as b goes to infinity, just like for every improper integral, 0 to b e to the minus 3x times dx. And now let's take this integral. You could do a u sub, but I feel like we're good enough to skip the u sub. So the derivative requires you to multiply by the chain rule, but in this case, we're going to multiply by the antiderivative, or multiply by the reciprocal of the derivative of the inside, because we're taking an antiderivative. So when we take this integral, instead of writing e to the minus 3x, because the antiderivative of e to anything is e to that thing, instead of multiply by negative 3, that would be the chain rule. What we're going to do is multiply by negative 1/3. We're going to divide by negative 3 instead. So it's going to be negative 1/3. Then we're going to plug in b and 0, where b is going to infinity. So it's going to be top minus bottom. But hopefully you know that e to the negative infinity is going to be 1 over e to the infinity. So that's 0. So this quantity is actually going to be 0. And then it's going to be minus, because you're going to plug in the bottom thing, fundamental theorem of calculus. So when you plug in 0, looks like it's going to be minus negative 1/3, because e to the 0 is 1. So it looks like we get our final answer of 1/3. So again, this is the remarkable thing, because when you're taking this integral, even if it's an infinite region, the area of this is 1/3. But this was just a nice practice of improper integrals. Again, it could appear on the BC exam, but that concludes our video on areas. So what did we talk about today? Well, we talked about that the integral formula is really easy. It's just the integral of top minus bottom, where you choose x coordinates. And you just do that integral, potentially using a u sub, whatever you need to do. Most likely, you're just going to type it in a calculator. So we saw some weird variations, which is the y integrals. So just keep in mind that instead of doing top minus bottom, when you have y's, you do right minus left, and then you choose y coordinates. Your first instinct, of course, is to do top minus bottom, because those are maybe 80% to 90% of the questions. But if top and bottom changes throughout the question, you might have to resort to turning it into y's. We also saw the equal area question with the calculator. When you have a calculator, just try to find your intersection points as quickly as possible, and then do the integral with the calculator, of course. And then the equal area one's pretty easy. It's just 0 to, or the first number to k, and then k to the second number, still top minus bottom consistently. Finally, we did an improper integral just to have some fun, just to cover every single area question imaginable. So for these improper integrals, when you have unbounded region, just the BC topic, it's the same thing, but instead of going from a number to a number, you're probably going from a number to infinity, and you just do this integral, potentially using the B process. So hopefully this video has been useful for you, but if you want more practice with areas, either with calculator or not, with improper or not, with equal areas and things like that, be sure to check out our Girls Teach Calculus video, which I'm going to link in the description below, where one of my former students has practiced several of these questions, questions that are similar to the ones I did, but you might think that she's a better explainer than I am. She probably is, now that I'm stuttering a lot. But check out that video if you want more practice. But again, this is the first lesson of our area and volume unit, so be on the lookout for our big videos on volume, volume by revolution, and volume by cross sections. Hopefully I'll see you there. Give us a like and subscribe if this video was useful for you, but I hope to see you in that volume by revolution video. Thanks again for watching, just like normal.